Hello everyone, today I'm going to run you through electric current and drift velocity. So we are mainly focusing on conductors today and how electrons pass through them. And a better word to use is drift through them. That's what we're going to use, drift. Electrons, they may be very, very small, moving at speeds close to light speed. But as they progress or drift through a conductor, we're going to see that they have actually a very relatively low speed. Some of them can drift quite slow, depending on the electric current. So to generate electric current through a conductor, first we're going to move you down to just to consider a circuit diagram component for a battery. If you consider that circuit, make a very simple circuit. There's no resistors in this circuit. It's just a conductor connecting one side of the battery to the other, the positive terminal to the negative. So the electric field produced in this circuit would go from the positive toward the negative. So in the conducting material down here, along the sides and the top and around, consider that conducting material there. There will be an electric field that goes out from the positive and in towards the negative terminal of that battery. That battery a little bit bigger there. So there's this electric field going to the left in this bottom segment. It would be pointed up in that side segment, to the right over here and down. Now the electric field is going to now be applied to our zoom in on a segment of this circuit. We can see how we're going to just take a little segment of this conducting material here and focus on it in this segment. So the electric field is applied from left towards the right in this scenario. So this is, think of it like a positive side and a negative side. So if we did have an electron in here, it would be attracted to the left as the electric field is applied to the right. So there's going to be this drift of electrons progressing through this segment of the conductor. Now, what we're going to need to do to examine drift velocity is just look at a small segment of that conductor. Consider it like a small slice of pepperoni in a long piece of, or long chunk of long sausage of pepperoni. Okay, so there's just a little slice that we're taking out of it. It has a little width dx, we'll call it dx there. And also, if you consider that electrons are passing through it, there's a small amount of charge dq. I'm using a capital Q here, passing through that. Bringing the light a little bit better here. As you've probably done before in a previous unit, you probably considered that this whole segment of this sausage here, this pepperoni sausage, has a charge over volume ratio. We can call that sigma, charge over volume. So the, excuse me, not sigma, that would be rho. So that would be the volume charge density. But for this little piece of it, a dq would be spread over that volume. Now the volume of this little tiny slice of pepperoni here, the little dq, is the cross-sectional area times, think of a cylinder here, cross-sectional area times the height of the cylinder, which would be dx, a dx. Now, how much charge is in there? Like, what is that little dq worth? Well, another way to look at Q over V is the charge of an electron. I'll call it Q little e. That is the elementary charge. That's what it's going to turn out to be. Times what I'm going to define here is a letter N. Well, N is the best way to define it is the number of charged particles per unit volume. and volume is going to be measured in meters cubed. Okay, so if we've got a number of electrons per unit volume within this pepperoni or within the entire pepperoni sausage of a conductor, I should probably stop using that metaphor. Okay. Then the number of electrons in that unit volume times the charge of an electron will be the charge per volume. So this ratio will be the same. Now if I take all this stuff here, dq over a dx equals charge of an electron times n. Now just to make this more generic, this may not be electrons. We could be looking at the drift of other kind of charged particles. If we get into a plasma, this could be a drift of protons as well. So it could be a lot of different things in a more general sense. But in terms of electrical circuits, this would definitely be the charge of an electron, or the elementary charge, 1.6 times 10 to the negative 19 coulombs. We take this and just spread it out a little bit. dq equals, we'll bring the area, that cross-sectional area, times dx up to the other side. Well, the charge times n. Again, I'm making that just more generic charge now. A dx. Okay. Now, if we start thinking about this, we've got electrons passing through, moving along at a rate. If we divide both sides by dt, we get a rate of charge. And we also get a very familiar rate of change of position over on this side. Now this quantity here, I want to define, this rate of charge is what we're going to define as I, the current, electrical current. Okay. Now electrical current does have a unit of amperes, so it's measured in amperes. All right, now if you look at an ampere, 1 ampere would be 1 coulomb per second. All right, so that's its definition. All right, so moving ahead here, let's scroll up a little bit. We've got I equals QNA, and now this dx dt is referencing a velocity. So what is this? This is the velocity of the body of electrons moving through the wire, moving through the conductor. So what we're going to do is define that dx dt as the drift velocity. That's where it appears, the drift velocity. All right. So this dx dt we're going to generalize as v sub d, the drift velocity. All right. So there we have it. This is a connection between electrical current, a very measurable value in electronics, to the velocity of an electron as it drifts through, or the velocity of the body of electrons as they move through. So as an example, if we've got a 10 ampere current, it's also shortened to amps, 10 amp current. Q is for an electron, which is the elementary charge. Okay. And let's take now, we need to be a little bit more specific here. A copper wire, so the N value, the charge, the number of particles per unit volume of copper has been measured and determined to be about 8.5 times 10 to the 28 electrons per cubic meter. Okay, so that's a measurable value. If you look it up on a chart or a book, you're going to find that value for copper. Aluminum has a different N, gold, platinum, all those different metals will have a different N value. But for copper, it's 8.5 times 10 to the 28. And let's see, we got a we need to define our wire here. So our wire might have some kind of length, but let's give it a radius of, make it real small. Some of those wires can be tiny. Let's go with a millimeter. Okay, which we'll have to define as 0.001 meters. So we can determine a drift velocity from this. Move it up here. So what is our drift velocity going to be? So we rearrange this. We're going to have an I divided by the E, N for copper, and A. So we got a current defined as 10 amps. E is 1.6 times 10 to the negative 19 coulombs. The N value, 8.5 times 10 to the 28 particles per cubic meter. And A, now A we're going to assume here a cylindrical wire. So the A is just going to be pi r squared. Pi times r squared. There's a lot in that denominator there. Okay, calculate that out. Take a few seconds. Delete. I'll show you what I'm doing here. Oh, that doesn't turn out too well. So I will save you the difficulty there. Plug in my value. And unless I'm wrong, I hope I'm not because I'm trying to do this in one take, 2.3 times 10 to the negative 4 meters per second. So as you can see, that's not a very fast velocity at all. When you're talking about the speed of light, 2.998 times 10 to the 8 meters per second. This is extremely small. I don't even know if I could roll this pin that slowly. So there we have it, drift velocity, electric current. Try out a few examples.